Velocity versus time graphs, V and T. Actually, my favorite graph, contains a lot of great information. We're going to take a look at it for the first time. But to get there, we're going to go with our familiar friend, the position versus time graph. But that's what this is. X in meters on the vertical axis, and on the horizontal axis we have time in seconds. Okay, so we've got a simple motion here described by 3 different phases. During the first 10 seconds, the object, whatever it might be, is traveling at 1 meter per second. Well, how did I get that? Of course, I applied the definition of velocity, which is the change in displacement over change in time. X minus x naught over t minus t naught. That's our old friend. Okay, so basically what that means is I found the slope and it's 1 meter per second. The slope of the flat section over here from 10 to 20 seconds is 0 meters per second, because 10 minus 10 means no change in displacement. We've maintained our position here. And during this leg of the motion here, we have negative 1.5 meters per second velocity. Again, by applying this same definition for velocity, change in displacement over change in time. It's exactly what I did, same technique, and it's negative 1.5 meters per second. Because each of these slopes are constant within their respective time intervals, that also implies that there's constant velocity here, then it changes, but it's constant velocity over here, and then it changes again, but it's constant velocity over here. So the intervals themselves are constant, even though we have multiple intervals, and of course we have, as a system, an overall change. But constant slope is constant velocity. So what I'm going to do is encode that information in a different format. It's called velocity versus time. On the vertical axis, I now have this variable here, v, and the units are meters per second. And what I have over here is time in seconds. Same axis as before. It's still a versus time graph, but now it's velocity versus time. So what I want to do is just translate this information here to the new type of graph, velocity versus time. It's a representation of motion information a different way. And sometimes seeing things differently can be very powerful. Actually, v versus t are really great for when we have something called a changing velocity. That's known as acceleration. We'll get to that at some time. Okay, so during the first 10 seconds, there's a constant velocity of 1 meter per second. Constant because of the constant slope again. So what I'm going to do here is just represent that as a horizontal line that is constant for 1 meter per second over these 10 seconds, like that. This represents this exact motion, just translated into velocity versus time. Well, notice that there's no velocity here from 10 to 20 seconds. So what do? I bring it down to 0. It's 0 meters per second. So I'm actually going to draw it like that, okay? And during the last piece of travel, the velocity is a constant negative 1.5 meters per second. And so I'm going to find 1.5, that's kind of here, and make it like that. And so we have this representing the motion here of negative 1.5 meters per second. So I'm going to label that just so we know what it is. That's 1 meter per second. This is negative 1.5 meters per second. So believe it or not, this information says exactly the same thing as this information. In fact, in a moment, I'm going to show you how we can go backwards from velocity versus time to position versus time. And I'm going to use the same example and show you the techniques to bring it back like this. That's what we're going to do. And so here it is, the graph that we just created. What we're going to do is bring it back to position versus time. Yes, we can. Yes, we will. We got to talk about some of the features of graphs in order to do it. So far with graphs, we've been studying slope, 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 and it's very, very important. Slope is rise over run. In a position versus time graph, rise over run, that slope gives us velocity information. Okay. Well, in this case over here, if we're going to bring it back to position versus time, we've actually got to look at another feature. It's called area, the area bounded by a v versus t graph. So here's how it starts. I've solved this equation from before for displacement. So the slope of a position versus time graph, which relies on the equation that we've seen already for velocity, that standard equation for velocity, I've just rearranged it and solved for displacement, which is delta x. So delta x equals v bar times t, the average velocity times the change in time. So what happens here is that the velocity, which is on the vertical axis, represents the height of this graph, and the base is represented by delta t. And so we noticed that we created a bunch of triangles, rather rectangles before. Yeah, these are rectangles. I'm pretty sure that they're not like this. They are definitely rectangle-ish. They're very rectangles. So this rectangle over here, if we wanted to find the area of this rectangle, it would be base times height. And so what happens is that it has meaning. This area, the bounded area in a v versus t graph, represents the displacement of an object in motion. Well, how does that work? Well, if we look at this, we notice that the base is in seconds. So we've got 10 seconds over here, and the height would be 1 meter per second. Well, 1 meter per second times 10 seconds gives us 10 meters. Quickly over here, since I ran out of space, we notice unit-wise this totally works out. If I multiply meters per second times seconds, I'm left with meters. That's the unit that I'm left with. That's the stuff, the quantity that we're looking for. We want to go and translate this into position versus time, so we need displacement information. This is the displacement, 10 meters. Over here, the displacement is negative 15 meters because the area of this rectangle, base times height, gives us negative 15. The negative is important. Again, the negative just indicates backwards travel. This is a negative velocity, so we're moving backwards. And of course, I'm going to mention it, but I probably didn't need to, but between 10 and 20 seconds, there's no area. This is a line. There's no area bounded by a line. Lines have no area. So the velocity here is 0, therefore the displacement is 0. So what I've done is dotted the relevant information, and then we're going to connect them. It's important to do that if we're going from velocity versus time to position versus time, to make the dots and then connect them, because when we incorporate acceleration, we're going to have some funkiness in terms of curving slopes and curving features, but right now we don't have to worry about that, okay? So because this is a constant velocity, due to the fact that it stays the same from 0 to 10 seconds, we can draw this here as a straight line from, well, it started at the origin to this position over here at 10 meters, okay? This is a constant slope, that would be a constant velocity, okay? We have no velocity from 10 to 20 seconds, so we maintain position like that. And from here, we're going backwards at negative 15 meters. So that's the displacement, okay, so from previous position. So all those exercises we did before really come in handy, because now we're gonna go negative 15 from our current position, so that brings us to negative 5. So my displacement of negative 15 relative to previous position brings us to this over here, which is at position negative 5 meters. And I would just connect this, giving me a constant slope because of the constant negative velocity here, moving backwards. And you'll notice that, there it is. We have the same graph as before. We brought it back from velocity versus time to position versus time. So we're gonna have some practice doing that, and it's a very useful skill to represent information, represent in many different fashions so we can understand motion that much deeper. Oh, we did it. Thank you, man. All right, Morad out.